All right, so we're still working on ellipses here. So in an ellipse, you have two foci, and you have a major axis, the long line through it, and the minor axis this way. We also have some very special points on the ellipse. So as the planet is going around the outside, this is the planet's orbit. When it's closest to the sun right here, we call this perihelion. When it's furthest from the planet, which would be the opposite side of the major axis, that point right there, it's called aphelion. Okay. Now this also depends on what you're going around. Remember, helios means sun, that's Greek for sun, so perihelion means closest to the sun. Aphelion means furthest from the sun. Now if you're going around the Earth, like the moon going around the Earth, this would be perigee and apogee. If you're orbiting Jupiter, this becomes perijovian and apjovian. If you're orbiting stars, this becomes periastrum and apastrum. So it changes with what you're orbiting. For solar system objects that all are going around the sun, we talk about perihelion and aphelion. Okay? All right. So far, so good. Now, we can also split this. So we split the major axis in half. We call this A, the semi-major axis. And we split this, the minor axis, in two parts too. We call this B, the semi-minor axis. Okay? All right. Second one. The radius vector of a planet sweeps out equal areas in equal times. All right, this is kind of a complicated way of saying something, but let me see if I can explain it. So here, let's have a planet right here. Here's the planet. A radius vector is a line from the sun to the center of the planet. Okay, and the planet's going around like this. Let's say 1 month later, it moves from this position to this position. So now the radius vector is up here. Okay? Then, what it says is it sweeps out this area, this crosshatch area in here. So as it moves, it sweeps out an area. What this really means is if I do the same thing over here, where I have a really long radius vector, it doesn't move as far, so this is 1 month later also. Because it's a long skinny triangle, and the crosshatched area in here, that area equals that area if this time equals that time. That's what it's saying. This is a very complicated way of saying that when we're closest to the sun, which is at perihelion, we're going fastest. When we're out here, we go very, very slow. Okay? A good example of this is Halley's Comet. Halley's Comet goes around the sun. Here's the sun. But the Halley's Comet goes around like this. I mean, it's not anywhere close to a circle. It takes 76 years to go around. But inside of Mars's orbit up about here, it does all this in less than 2 years. The remaining 74 years is spent going all the way out to Neptune's orbit. So what happens is it goes really fast, whips around the sun, and then it slows down and it almost stops right here. And then it free falls back in around the sun. Same thing happens here, is as you're going close to the sun, you get a slightly higher gravitational pull from the sun, and so you're actually going faster here, you slow down, and then you go faster around here. That's the thing about for the Earth's orbit. We're perihelion, where it's actually closest in January, early January. So in early January, we're going the fastest. In July, 6 months later, we're going the slowest. Yeah. Now, the Earth's orbit is very, very close to being a circle, so we don't really notice much effect. But it does make a significant effect on planets like Mercury and Mars, which have a more eccentric orbit. So let's talk about eccentricity here. So remember, this is Kepler, this is all ellipsis. Eccentricity is a measure of how flattened your curve is. Like that one is, Halley's Comet is very eccentric. So E squared equals 1 minus B squared over A squared. Okay, what are B and A? Well, B and A are these values right here. Yeah. So let's look at this. If it was a perfect circle, then B and A would be equal, right? And both of the foci would be at the center. They'd be on top of each other. And if B and A are equal, then this becomes 1. And what's 1 minus 1? 0. You take square root of that, it's 0. So the eccentricity equal to 0 means you have a circular orbit. Now in the other case, what if we say, oh, we're going to have one foci here, where the sun is, and we're going to take the other focus and we're going to send it out to an infinite distance away, since we're going to stretch out the ellipse. Well, then this number becomes really super huge on the bottom. And if the number on the bottom of refraction becomes very, very huge, B doesn't change, this goes to 0. And then E just becomes 1. And in that case, you actually get a parabola. So ellipses have an eccentricity greater than or equal to 0, but less than 1. If it's 1 or greater, then it's not an ellipse anymore. It becomes a parabola or a hyperbola, depending on how much energy it has. So the Earth's orbit is like 0.05, so it's very close to being a circle. Halley's Comet has an eccentricity of 0.76, which means it's much closer to being parabola type shape. So every time we determine the orbit of an object, we figure out what its eccentricity, and that tells us how flattened the ellipse is. Number 3. P squared equals A cubed. What's that mean? It's just a mathematical equation. This is the period in years. This is the distance in AUs. And this equation only works if you're going around the sun. If you're not going around the sun, you have to add some other values in there, and that's what Newton did later. But right now, you do it in years and you do it in AUs, and it works out just fine. So let's think about this. If I had a planet with a distance of, let's say 4 AUs. Okay? So its semi-major axis, A, which is half the distance of the major axis, it is also the average distance. So for the Earth's orbit, the average distance is actually 1 AU, by definition. So as a distance of 4 AUs, I just plug this into my equation. P squared equals to 4 cubed. Well, remember, P squared is equal to 4 cubed means 4 times 4 times 4. And then we take the square root of that. Well, 4 times 4 is 16 times 4 is 64. And the square root of 64 is 8 years. So if we had a planet at a distance of 4 AUs, it would take 8 years to go around the sun. So it's a fairly simple thing. You just plug it into this formula right here. If you know P or if you know A, you can figure out what the other one is. All right. So those are Kepler's 3 laws of planetary motion. All planets orbit around elliptical orbits, sun has one focus. And this isn't just for planets. This is anything going around the sun. And it goes fastest when it's closest to the sun, slowest when it's furthest away. And P squared equals A cubed, which means you make A bigger, P gets bigger. So the planet's closest to the sun, like Mercury, goes around in 88 days. So it has the shortest period. It also has the shortest distance. And then it gets longer as you go out. When you get out to planets like Neptune, you're talking 70 years. I mean, over 100 years. I think Uranus is like 80 years. So you get much further as you go out. Jupiter takes about 12 years. Saturn takes about 30 years to go around. So, further out you get, the longer it takes to go around, the slower you move. and the bigger distance you have to cover. All right, what did Kepler look like? Here is a drawing of Kepler, or painting of Kepler. Let it warm up here. Turning off the extra light too. So here is Kepler. Notice the big collars, that was the thing back then. This is pretty much what we think he pretty much looked like. Notice he had a compass for measuring the size of the solar system. This was a page out of his book where he was trying to do the nested perfect solids, which I was talking about. Very elaborate, very cool, but it didn't really actually end up being anything in reality. All right. Oops. Sorry, getting ahead of myself there. And that gets us to our next guy, which is in the next video.